Last class, also before we start, great news. We got the new mic. Hopefully no more popping, so you don't have to make me #mute style. You can actually listen along, unless the sound of my voice makes you upset, and then don't do that maybe. We want to predict the molecular geometry of this ion, the SO32- ion. Hopefully you've thought about it once, maybe even since we had our class last time. In order to predict the shape, the molecular geometry of the sulfite ion, we need a Lewis structure. So we have to come up with a Lewis structure for it. We've got sulfur. We've got 3 oxygens. These each have 6 valence electrons. What else do we have that contributes electrons? We've got a 2-. So the 2- charge also means that we add 2 electrons. We'll call them VEs. So we have 20 valence electrons, not 20, 26 valence electrons. For our shape, we are going to get the best shape if we put the sulfur in the middle. This will give us the most symmetry. We need everything to be connected in order for this to make a shape, and so we're going to put some bonds in, just getting our oxygens connected to our sulfur. This is all the bonds we're going to add, because if we add more bonds, then we have triangles, and triangles love to explode, and we don't want that. So -6 for the minimum number of bonding electrons. That means we've got 20 remaining electrons, 20 electrons left to place. Where are we going to start placing those electrons? Are we going to start on the inside and work our way out, or are we going to start on the outside and work our way in? We're going to start on the outside and work our way in. So we're going to start by giving all of these oxygens electrons until their what is full? Piggy bank? No. Their octet, yes. Lots of people got it. Good work. Thank you. So we're going to fill up their octets. That means that we can give them each 6 more electrons. 6 times 3 gives us 18 electrons to our oxygens. That means we've got 2 left, and those 2 left can go on to our sulfur. And now all of our electrons are spent. They're all on the board. We can check for octets. Our oxygens have 2, 4, 6, 8 electrons. They all have the same configuration, so our oxygens are all happy. Our sulfur in the middle has 3 bonds. Each of the bonds, since they're single bonds, is 2 electrons, so 3 times 2 is 6. We add another 2 for the lone pair, and our sulfur also has its full octet. This is incorrect. Why is this not correct? We're missing our brackets with the little charge in the top right corner. That's all we're missing. So big brackets and a 2- in the top right corner. And now it's done. It's complete. So this is our Lewis structure. This is just to start us getting our molecular geometry. Now we need the molecular geometry part. So how many groups do we have on our sulfur? How many electron groups are attached to our sulfur? 4. We have 4 things on our sulfur. We've got lone pair, lone pair, lone pair, bond, 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 lone pair. We've got 3 bonds and 1 lone pair for a total of 4 electron groups. 4 electron groups, if they were all bonds, would be our tetrahedral shape. But we have 1 lone pair, and so that's going to make it trigonal pyramidal. Right? Gestures in valence shell electron pair repulsion theory bonding or posing. So this is trigonal pyramidal molecular geometry. Questions at all? Just like to give us another reminder that watching somebody who knows what they're doing often makes it feel like we also know what we're doing, and that's not necessarily the case. It can be the case, but you should also be trying to do some of these either through homework problems on your own, or through the practice quizzes on Canvas, or through our book online, or some other textbook that gives you problems like this, so that we can find out if we're actually confused. And if we are confused, we can ask me, or we can also go to Logan for his SI sessions and get help. All right, when we are representing molecular geometries on paper, there's a system for that. Perhaps to nobody's surprise, we have a system for, it seems like, everything. And so on paper, chemists will use this notation for bonds. So we're showing our bonds. And this gives us 3D space. So normally everything we've been drawing has been flat on the board, or we would have to imagine what it looks like. Sometimes we want to convey the 3-dimensionality of chemicals that we're drawing. And so we use these lines. We've got straight lines. These lines are all bonds, by the way. So the straight line is in the plane of the board. So it's flat on our paper, or it's flat on the screen. We also have a hashed line. And the hashed line means that it's going away from us. And then we've got the wedged line, which is coming towards us. And the way that my brain remembers this is that wedge makes me think of potato wedges, and I really like potato wedges, and so I want potato wedges to be coming towards me, because if potato wedges are coming towards me, guess where I can put them? In my cargo pants, so I can save them for later. No, in my mouth. So the wedge line's potato wedges. I want to eat potato wedges. It also sort of looks like pizza. Your pizza should not look like a hashed line, or something's very wrong with your pizza. But a wedge line could also be pizza. Lots of people like pizza, so maybe that works for you. And we can draw the major molecular geometries that we've talked about in any of these ways. We're not really going to do much with these lines, but you should know that they exist. These are just like one way that you can draw each of these. You could also rotate them as many times as you want. There's really uncomfortable ways, I'll say, to draw some of these, where it just really hurts to think about. These are hopefully the easier way of thinking about them. Okay, to build on our molecular geometry, because surprise, surprise, we're not done building. There's a little bit more. We are going to talk about electronegativity and polarity, and this is going to add another concept on top of our molecular geometry. And our molecular geometry is stacked on top of our Lewis structures, and our Lewis structures is stacked on top of other concepts, which are stacked on top of other concepts, which are stacked on top of other concepts. So we've got a lot of building going on, and we need to make sure that we've got all of those concepts in place to be able to arrive at the peak of what's coming out of electronegativity and polarity. So you may know that if you combine water and oil in a container, even if you shake them up, eventually they separate out into 2 distinct layers. And there's something about the water molecules and the oil molecules that causes them to separate out every single time, regardless of how many times you shake them up. And that something has to do with electronegativity. So in oxygen and hydrogen atoms in water, these are each contributing 1 electron into this bond. Hydrogen gives its 1 electron into the bond, oxygen gives 1 of its electrons into the bond. And so in theory, they're sharing that bond. They're sharing it nicely and evenly and fairly. However, that's almost never the case when sharing is occurring. And as it turns out, the oxygen takes more than its fair share of the electron pair. So what this means is the electrons in the OH bond are not split nice and evenly between the two of them. They live closer to the oxygen. If you have siblings or if you have cousins and anyone's ever bought you a present and said, this is for you and your siblings, this is for you and your cousins, you all need to share it and use it the same amount. And especially if it's like a gaming console or something, that's what I have experience with. It's almost never shared evenly. There's always somebody that gets to play more than you, or maybe you get to play more than somebody else. That's what's going on here. They're not sharing evenly like they're supposed to. It's unfair. And nobody's going to step in because that's just the way it is. So the word that we have for this is electronegative. So oxygen is more electronegative than the hydrogen, which means that it pulls the electrons in closer. That's what makes it negative. Electronegativity is our ability of an element to attract electrons within a covalent bond. Remember that a covalent bond is a shared electrons bond. We're sharing those outermost electrons. Electronegativity uses a relative scale. This isn't to say that we've got cousins and aunts and uncles. It just means that we arbitrarily set the maximum value, and then everything else is compared to that. Fluorine has the maximum value for electronegativity, which is 4.0. It's the same as our GPA scale. There's no AP classes for electronegativity. So fluorine up in the upper right-hand corner of our periodic table, not all the way up in the upper right-hand corner, but up towards the upper right-hand corner, has the maximum value of 4. And if you have your yellow sheet along with you, then you should be able to see somewhere on that yellow sheet in the box for fluorine, there's a 4.0 in that box. That is the electronegativity value. It's also there for everything that's down and to the left of fluorine. So you've got all of your electronegativity values on that yellow table. The only one that you should have memorized is fluorine. That's the one electronegativity value that I expect you to have. I don't know that you'll be tested on it, but that's the one that you're expected to know. The other ones, it's sometimes convenient to know them, but you'll be given them. So the way that electronegativity works is that because of the unequal sharing, the oxygen atom has a partial negative charge, and we symbolize that with a lowercase delta. And the hydrogen atom has a partial positive charge symbolized by delta plus. The result of the uneven electron sharing is a dipole moment. The di prefix meaning 2, and pole, like north and south pole, where Santa and bears live, respectively, but also on a magnet. You may know that magnets often have one side that's positive, one side that's negative. We call those north and south poles sometimes. So we get a dipole moment, we have a small magnet moment. So our oxygen would be on this side, our hydrogen would be on this side. The hydrogen has less electron density than it is expected to have, and so it's partially positive. Oxygen has a little bit more electrons than we would expect it to have, and so it has a partial negative charge. Do we have questions so far about dipole moment or electronegativity? Another way that I usually think about this is that the electronegativity scale, this is like a tug of war stat for our atoms. So all the atoms have an inherent tug of war stat for electrons. And if you've got a really high electronegativity value, that means that they're very big and very strong, and they can really pull on those electrons and steal them away from other things. And if you've got a really small number, that means you're a not very strong person, not very strong atom, and so you cannot pull those electrons very strongly, and you'll get your electrons taken sometimes. Covalent bonds that have a dipole moment are called polar covalent bonds. So polar meaning having poles like north-south or plus minus. It's a polar covalent bond, the polar meaning that it has the positive and negative sides, and the covalent means that we're still sharing the electrons. The larger that the electronegativity difference is between the two elements, the greater the dipole moment is, the more theft is occurring, and the more polar that the bond will be. We also have two other options. It's not always just going to be polar covalent. We've got two other options that we'll talk about in a bit. So here is electronegativity, as I make the projector black out repeatedly. Loading, loading, loading. We're loaded. So we can see we've got fluorine, top right corner 4.0, next highest oxygen 3.5, chlorine, nitrogen sort of tied at 3.0, and everything gets lower as you move towards the bottom left corner. So generally, if you're fluorine, that's going to be the highest. If you're close to fluorine, you're going to be a higher electronegativity value. The further away you get, the lower that number gets, generally speaking. Here's one of the other options that I alluded to earlier. If two elements in a covalent bond have the same electronegativity, the electrons are shared equally, there is no dipole moment. And we call this nonpolar. So nonpolar means that we have no dipole moment. Or means that we have evenly shared electrons. In the bond. This is going to occur anytime we have the same two elements. So anytime something's bonded to itself, it's always going to share perfectly equally because they have the same tug of war stat for the electrons. So they're going to pull the same amount, they're going to share it nice and evenly. So that's our nonpolar covalent bond. They're still sharing the covalent bond. Sometimes you might also hear this called pure covalent. It's idealized sharing of electrons. On the other hand, if we have a large electronegativity difference. The electron is completely transferred, and the bond is ionic. So this is a new definition for ionic. For ionic, we have a large electronegativity difference. I'm going to abbreviate that as En. We will also still be able to use our metal plus nonmetal definition, though. Typically, if it's a bond between a metal and a nonmetal, it's still going to be ionic, even if we don't have a very large electronegativity difference. Now you might be thinking, what's a small electronegativity difference? What's a large electronegativity difference? What's a medium electronegativity difference? I jumped the gun a little bit. Our intermediate is the polar covalent. I'm going to skip over that to our table. So these are our general guidelines for nonpolar, polar, and ionic. So an electronegativity difference of 0 to 0.4 is pure covalent or nonpolar. If you're between 0.5 and 2, that's polar covalent. If you're above 2.0, it's likely ionic. So the numbers 0.4 and 2.0 for our differences, those are our cutoff points. These are just approximate guidelines. It's really on a continuum, but to be able to classify things, we put some numbers to it. So below 0.4 is nonpolar. Above 2.0 is ionic. Polar is in between. You don't necessarily have to have these numbers memorized, but they would be convenient to have memorized. So on top of our 4.0 being fluorine, fluorine's our straight A student, gets a value of 4.0, that's our highest value. We also might want to remember 0.4 and 2.0 for our cutoffs for nonpolar and ionic. All right, using those 0.4 and 2.0 and your yellow sheet, assuming that you have it, please classify these bonds between these pairs of atoms as pure covalent, aka nonpolar, polar covalent, or ionic. All right, to be able to classify these bonds, we need to know their electronegativity values. Our yellow sheet is a great resource for that. On an exam, you'll be given electronegativity values for them if I think that you need to know them. Sometimes I won't give them to you because I want to test you on a concept without the numbers. So to start with these, we need our electronegativity values. So we're going to look them up. For nitrogen, it's got a value of 3.0, a straight B student. For RB, we have a value of 0.8. For chlorine, we have a value of 3.0. Phosphorus is a 2.1. Oxygen is 3.5. On our yellow sheet, it's the number in the bottom right corner of each of the cells. Some of them don't have a value there because they don't really bond, notably our noble gases. So we can calculate our difference in electronegativity. It's just the first electronegativity minus the second electronegativity. It doesn't really matter what order you put them in. If you get a negative number, just make it positive, because we just care about what the distance is between them. So we'll make it a little more robust and add absolute value bars. So for nitrogen and nitrogen, they're the same thing, so we would expect, regardless of what element it is, 3.0 minus 3.0 gives us 0.0. So that is going to be which of the three options? Pure covalent. Idealized sharing of electrons, no dipole moment, no positive, no negative, perfectly balanced. Between Rb and Cl, 3.0 minus 0.8 gives us a value of 2.2 for our difference in electronegativity, our delta En. Which of the three options is that going to be? That is going to be ionic. We could also tell that it's ionic another way. What's the other way that we could tell that it's ionic? It's a metal and a nonmetal. So Rb is a metal. Chlorine is a nonmetal. So we could have also predicted that it would be ionic based on those facts, based on being metal and nonmetal. With nitrogen and nitrogen, we could have known that it's nonpolar or pure covalent because it's the same element. So that would be our non-calculation method of figuring it out. For P and O, we're going to do 3.5 minus 2.1. We get a value of 1.4 for our difference in electronegativity. And that's going to be our polar bond. It's between 0.4 and 2.0. Bonus conceptual question. In the bond between phosphorus and oxygen, which side, phosphorus or oxygen, is going to be partially negative? What do we think? We've got a guess for phosphorus. Are there any other guesses? The other guess is oxygen. We've hit the two expected outcomes. Any other guesses? It's a trick question? No, it's not a trick question. It's going to be oxygen. So oxygen gets the music note minus, phosphorus gets the music note plus. The higher electronegativity gets the electrons. Not completely in the case of polar covalent, just partially in the case of polar covalent. So we might sometimes represent this as like a lopsided bond, where this is the probability of where we're likely to find the electrons. They're more likely to be found on the oxygen side because it's pulling on the electrons stronger. This might be cringe, but phosphorus is getting electron mogged. That's essentially what's going on. I feel like it's current. It's kind of in the zeitgeist. Okay. So this is building up to another concept. Polar bonds do not always mean that the entire molecule is polar. So we're using these polar bonds to build up to polar molecules, figuring out if molecules are polar. A polar molecule is going to have a net dipole moment. Overall dipole moment across the molecule. Remember that a dipole moment is that music note plus, music note minus that we were looking at. Spread out across the molecule. If we have a diatomic molecule, meaning that it's just two atoms bonded to each other and it has a polar bond, it will be a polar molecule. If we have more than two atoms, then the polar bonds can cancel each other out. So they can cancel out across / in a molecule. And we've got a couple of ways of thinking about this. One of them you're probably not going to like, and one of them you'll probably be able to use. As an example of canceling out, carbon dioxide, carbon in the middle, oxygens on the outside. Carbon has an electronegativity value of 2.5, oxygen's a 3.5. And so each of these bonds has a change or a difference in electronegativity of 1, and that would make it polar. Right, it falls between our 0.4 and our 2.0. However, they're pointing in completely opposite directions. So it's oxygens on the outside with the little tiny baby carbon in the middle, and the big, strong, burly oxygens on the outside, both pulling on the little tiny baby carbon in the middle. Carbon's just kind of hanging there, is what I imagine it. I'll draw out what I'm thinking of. I can't draw muscles, so sorry. And we've got the little tiny that's not curly enough. Little curly hair. And then we've got the big nope. It didn't work. Is there a flip option? Whoa. Sort of like that. Okay, so if this is what my brain does, this is what my brain decides to think about. The big, strong, burly oxygens on the outside are pulling in opposite directions, right? They should be leaning away from each other. So if they're both pulling, what direction are they all moving? They can't move out infinitely, right? Because there's something in between them holding them together. So it's just going to be essentially the force of the oxygen pulling this way versus the oxygen pulling that way. And since they're the same thing, those forces cancel out, which is what we're showing down here. So because it's linear and they're pulling in completely opposite directions, the difference in electronegativity cancels out across the entire atom. And we represent the direction that's being pulled with these funny looking arrows. And they look like that because one side is a plus. So these are the positive sides, and then the other side is the negative side. So electron pulled toward the oxygens, it's pulling out. The arrows that we draw on cancel out. And I'm guessing that we probably are not going to like the arrow method. It works really nice for linear. It doesn't work really nice for like tetrahedral when we have to expand into three-dimensional space. Do you have questions so far about polarity, nonpolar, polar, ionic? All right. So we can represent polar bonds with arrows or vectors. Vectors have direction and also magnitude. I think somebody's thinking of the Minions movie. So they point in the direction of the negative, and they have a plus sign at the positive, like I was showing in the previous slide. If they point in exactly opposing directions and they have the same size, then they cancel out. So representing this on a water molecule, oxygen on the inside has a 3.5, hydrogen on the outside has 2.1s. And so if we do the arrow method, the arrows are pointing towards the oxygen. And notice that the arrows are not quite pointing directly at each other. If they were pointing directly at each other, then they would cancel out. They're pointing a little bit off. They're a little bit up the way that we've represented them here. And so those aren't going to cancel out entirely. The left and the right part is going to cancel out, but the up direction part is not going to cancel out. So if we have a physics moment here and we separate these arrows into their vertical and horizontal components, the horizontal components cancel, the vertical components add up. This is part of why I was saying I don't think we're going to like the vector or the arrow method, because we get to do this, and it's more fun in three-dimensional space. There's a shortcut that we'll learn later. The long and short of it is the arrows don't cancel out in water. And so water is polar. Overall. Here are some common cases of dipole moments adding together. We've got some examples of things that are polar on the top. So we've got a diatomic compound with a polar bond. That one's always going to be polar. Not a polar bond, a polar bond. We've got this shape, which is trigonopyramidal. We also have this tetrahedral, but one of the bonds is different. You don't need to have these memorized. I'm just writing out explanations so we can see why that they're the way they are. And then for nonpolar, we've got trigonal planar with all the same bonds. And we've got tetrahedral, all the same bonds. And these two on the bottom, because they're all the same bonds and they're trigonal planar or tetrahedral, these ones are nonpolar. The arrows perfectly cancel out. We know that the arrows perfectly cancel out because the way that these shapes are made, valence shell electron pair repulsion theory, our groups are spreading out as much as possible. So fluorines are all spread out as much as possible. The arrows pointing in different directions are spaced out perfectly, and they're the same size, so they all cancel out. You can do the vectors if you want to prove it. Okay, so if we want to determine whether a molecule is polar, the first thing that we need to do, this is an important check. We want to determine whether the molecule contains polar bonds. The molecule can't be polar without a polar bond, at least one polar bond. So if you're given a molecule and you want to know if it's polar, first thing you want to do, refer to your electronegativity values on your yellow sheet or somewhere else. Figure out, do we have any polar bonds present? If you don't have any polar bonds, congratulations, it's nonpolar. We saved ourselves the time of thinking about arrows or doing our little shortcut that we'll talk about in a bit. And then we want to determine whether the polar bonds, if there's polar bonds, add together to form a net dipole moment. So we can determine the molecular geometry. If we wanted to, we can separate it out into vertical and horizontal components and in and out components, depending on what shape we have, to figure out if there's a net dipole moment. Alternatively, we can use the somewhat wordy Mrs. K's alternate method for determining molecular polarity. This has a shortcut name that I'll tell us in a second. So the first thing we need to do for this method is we have to look at the Lewis structure. So we have to come up with the Lewis structure. It has to be the correct Lewis structure. So we draw the Lewis structure. It will be nonpolar if both of these things are true. Our first check, no lone pairs on the central atom. What this means is we're going to have our shape be either linear, trigonal planar, or tetrahedral. Our molecular geometry will be one of those three shapes. Those are all perfectly spaced out. And if the atoms bonded to the central atom are all the same or have the same electronegativities. So same difference in electronegativity on all bonds. If both are true, nonpolar. So essentially what this is a shortcut for coming up with whether something's nonpolar. And so I think a fun thing to call that is the nonpolar express. All right, enough talk, time to try it. We want to determine whether CH4 is polar. What do we need to do to figure out if CH4 is polar? We need to draw the Lewis structure. I'm going to pretend like we're all perfect at drawing Lewis structures. Congratulations, we have the Lewis structure. There it is, CH4 in all its glory. Then we have to do what? Check if there's any lone pairs on the central atom. So our condition, first check, no lone pairs. Do we have no lone pairs, in this case, on carbon? No lone pairs on carbon? Check. Carbon just has 4 bonds. What's our second condition that we have to look for? The second condition is all bonds are the same. Are all the bonds to carbon the same? Yep, they're all carbon to hydrogen. Check. We met both conditions, so it's nonpolar. We can also determine whether NH3 is polar. What's the first thing that we need to do for NH3? Draw the Lewis structure. So again, I'm pretending that we know how to do Lewis structures. I'm pretending that we have it mastered. Boom, Lewis structure. Now, determine whether that's a polar molecule. Okay. Is it polar? Oh, we got people shaking their heads. We got people nodding their heads. What are our 2 checks that we need to do for the nonpolar express? 1, no lone pairs on the central atom. Is that true? False. Not true, not correct. So on point 1, the nonpolar express fails. So it is polar. There's another check that we should be doing before we even do the nonpolar express, and what is that check? Any ideas? Okay. Are the bonds polar? Do we have polar bonds? You have to have polar bonds to have a polar molecule. We've got nitrogen to hydrogen. Nitrogen is 3.0, hydrogen is 2.1, 0.9. This is a polar bond. So we didn't waste our time doing the nonpolar express check. But if you do this and you get a value that's below 0.4, then it can't be polar, which is mostly true. All right, determine whether SO2 is polar. What do we need to do first? We need to do the Lewis structure. So we do the Lewis structure. Oh, that didn't work out exactly. We do our Lewis structure. Congratulations, we did it. I think this showed up earlier in the slides, so we could have also gotten it there. What do we need to check for? Before we check for lone pairs? Do we have polar bonds? We've got sulfur bonded to oxygen. Sulfur is a 2.5, oxygen is a 3.5. Add some absolute value bars, so it makes it a positive number. You get a value of 1.0. Yes, it is a polar bond. And our arrows would be pointing out towards the oxygen. The way that I've drawn it flat like this doesn't represent the actual shape. So that's why the arrows won't actually cancel. In reality, it would be something more like this. If we draw it that way, we can probably see those arrows are not going to cancel each other out, right? They're both pointing down into the sides. So we're going to have a net arrow pointing down. But we can do our nonpolar express check anyway. Nonpolar express, if both conditions pass, then it's nonpolar. First step, no lone pairs on the central atom. True or false? It is false, so it fails. Right, we do have a lone pair on the central atom, so it fails, so it's polar. We could also reason through with the arrow method. Any questions at all about polarity? We will be working on this in lab today. One of the things that we're working on in lab this week is our molecular models worksheet, which requires us to do Lewis structures. And I think there might also be an opportunity for us to do some stuff with polarity. More importantly, we'll have time to play with molecular models. We're also going to be finishing up our alum lab. So So we'll be collecting our crystals. Hopefully we have crystals. And being able to wrap that up. So electronegativity and polarity both play into why water molecules and oil molecules don't get along. Water molecules are polar, somewhat famously so. They're very polar. Oil molecules are nonpolar. And so the reason that oil and water don't mix is that because water is polar, these partial positive and partial negative ends in the water sort of like stack up. They link up to each other. You can think of it like a bunch of little magnetic marbles we just threw together. They'll all clump up together and push out anything that's not also a little magnet. So all of the water molecules link up and they push the oil molecules out. The way that oil molecules, nonpolar molecules interact, especially oil molecules, it's more like weaving the pages of a phone book together. It's more like friction. They've got like long bits. It's sort of like spaghetti. If you've ever made spaghetti and you like let it dry out a little too much before you serve it, and all the spaghetti is like sticking to each other. You have to like detangle them. It's sort of like that. It's sort of like a friction sticky effect. The interactions between polar and nonpolar molecules are much weaker because these are just little tiny things. They're not long enough to have that sort of chemical friction effect. And the nonpolar molecules don't have any polar parts to latch on, to magnet onto the water molecules. So instead, what we use to wash away oil with water is soap. We add a little bit of soap, and soap typically has something that looks like this. So soap has a nonpolar tail or a hydrophobic tail. Nonpolar or hydrophobic, probably what you'd call it in biology, tail, and a polar head. So it's got a little polar section on the end. This end can latch on to water molecules. And the nonpolar tail connects to oil/nonpolar molecules. So this allows you to link water with oil or nonpolar molecules, and then when the water washes away, so does the oil. It pulls it with it. That's how soap works. I usually put a question about how soap works on the exam because I think that it's an important carryover into our daily lives to understand why soap works. Any questions at all about Chapter 7? We started with light, and now we're here. The saga is complete.